Hello everyone, welcome to this session. My name is Wycliffe, and in today's video I want to share with you how you can obtain satellite information for your sampling points. So let's say you've gone to the field and obtained some coordinates of where your experiments are, or where you made some observations or households or something of that sort. Provided you have some points from the field, you've walked around a region, obtain your coordinate data of longitude and latitude, but then you want, for example, spectral reflectance values for these locations over a period of time. So how do we do this? Let us jump into R. Okay, so inside R, we'll start by loading our libraries. The first library is ArcGEE. The second library is going to be MapEdit, because this is the library which is going to help us to obtain the coordinates information from a map layer. Okay, after we've loaded MapEdit, we load dplyr, because dplyr will help us to wrangle the data which we shall have obtained from MapEdit. And finally, we'll need a library called SF to convert our Earth Engine object into an SF object, and then we will use dplyr to clean it. All right, so we will start by initializing our Google Earth Engine account, which we use initialize to achieve. And once that is done, then we can draw the points of our interest. Sometimes for your case, maybe you've already obtained your coordinates in your phone, or you collected them using a GPS, or you obtained them from a colleague. Okay, so for us, we will draw points using MapEdit functionality. So I'm going to draw 26 points so that I can easily use letters to add them IDs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I've just distributed randomly within the T growing region. Okay. So after that, I click done, and now we have our points, which is an SF object in the 26 with 26 entries, right, or points, correct? So once we have our points, we can create we don't need all these IDs. We can have our own ID. For example, the names of these points, field 1, field 2 up to field 26, or point 1, point 2 up to point 26. For this case, I will use letters, and if you check letters, it is containing A, B, C, D up to Z, 26. That is why I chose the 26 number to digitize for easy entry in this session. Okay, so we'll take points, and then we'll mutate a column, and this column we can call it ID, and then we assign it the value from letters. After that, we only select this ID. All right, so we'll have the geometry column and only the ID, which contain letters for our simple feature. All right, okay. So after that, we will convert this our simple feature into an Earth Engine object. So our points will become SF as Earth Engine object using the points we had. Okay, so our points here is now a feature collection, which is an Earth Engine object, and we can use it to do the extraction of pixel values from our images in Google Earth Engine. All right, so let's get the Sentinel-2 image from Google Earth Engine. So we'll call it S2, and we will say this is Earth Engine object, which is an image collection. But then from the image collection, we look for dataset, and in the dataset, we are looking for Copernicus or S2SR. That would be easier. S2SR, right? That one. So once we have our Sentinel-2 image, we know that we will not use all the bands. So the only bands that we will use are the spectral bands. If you go to Google Earth Engine and you look for Sentinel-2 or S2SR, you will realize that it has got several bands, but we won't need aerosols, for example, or you can even keep it, but we would want to get band 2, 3, 4, 5, 6, 7, 8, band 8A, band 9, 10, 11 only. So we can only pick those. We can only pick those like this. Okay, so the bands we'll use, okay, let's even include band 1, band 2, depending on what you need. You will pick your own bands that you want to do. For example, in this case, we are imagining someone who wants to do a machine learning workflow or build a machine learning workflow to detect, for example, T fields or to detect something about the T plant. And building this machine learning workflow is normally easier, or we have more libraries within individual programming languages like in Python or in R than in Google Earth Engine coding editors, those that are provided by Google Earth Engine itself. So somebody might be interested in downloading all the images and then using them locally, right? Or extracting spectral values and bringing them locally. So those are the bands, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 bands, right? So after that, we know that this satellite image has got cloud problems. So we need to handle that by bringing the CS or Cloud Score Plus image. So where do we get Cloud Score Plus? It is an Earth Engine collection, image collection, right? And then $, we get dataset. From dataset, we look for Cloud Score, that one, okay? Let me extend this so that you can see all the full name. Okay, once we have that, then we need to ask ourselves, when is the start date for the image we need? Maybe for you, you only need for 1 day or for several months. So that is what you provide as the start date. Let's say 0101, and then end date, let's say 2025, 01 again, 01. So that's a 1 year image. Okay. So after getting that, we can now do our cleaning or filtering of our image. So we can make our Sentinel-2 image, which is S2 $, sorry. And then after getting the S2, we filter bounds. So we will filter bounds using our points, right? After filtering the bounds of points, we will get only images that intersect with the location of our points. And then we'll filter date. For the date, we'll put the start time, start date, and until end date, right? After filtering for the date period, we need now to link our collection with the CS plus image, which has got the CS band to clean our image. Okay, so each image will map a function on them to do the cleaning. So the function will take an image. After taking the image, it will pick the quality assessment band, or it will pick the QA. So this will be from the image we select the CS band, right? Which we provided up there. And then our image, we will update its mask, right? We will update mask. And in updating mask, we pick where QA is greater than 0.6, like that, okay? Then after that, we are only interested in the median for this period of time, okay? After getting the median for this period of time, we might only want to clip it to the points, right? But only the bounds of points, because points are not polygons. So we will clip to the bounds of that point, right? And then we can only then select the bands because we've created the list of bands here. Okay, so when we run that and we visualize this, for example, map $, add layer, we'll be able to see our image, Sentinel-2 image, and then we can decide also to add on top of it map.add layer, sorry, map $add layer points, like that. So we can look at our map where the points are. Okay. Okay, but we realize that if we just filter by the bounds or we clip to the bounds of the points, then it just fits to the minimum and the maximum value of the longitude and latitude for the points. So the good practice is to buffer these points so that at least there is some distance outside the T field or the T points or the points, right? So we'll do that and that. So all our points will be inside the image, not just the last pixel of the image, all right? So that should be way, way better with the image extending outside the points. Should be able to see that. It's taking some time. Plus points as to image, yeah, like that. But anyway, it's very black and we will improve that visualization, right? Or we can just say S2 image is our Earth Engine object. EE object is that, okay? And then we provide visualization parameters, which is a list, right? And inside this list, we can provide a minimum of 100 and a maximum of about 1000. These values depend on the image you are visualizing. And then we can also select the bands and say we are only visualizing the true color composite, which is band 4, band 3, and band 2, right? And then after that, we can then add layer for points, which is the Earth Engine object. EE object is point, okay? And then after that, we can provide visualization parameters. And then we say this takes a list. And in the list, we only provide color and width. So you can say color is, say, blue or even red. And then width, we can give it a width of maybe 12 or something is not right. List, we have double there, okay? Yeah, that should work. Okay, so if we zoom into our region of interest, we should be able to see the points and the image. Yeah, quite clear. So those are our points and that's our image because we buffered it. We buffered the points with about 2 kilometers distance from the points, right? 2000 meters, which is 2 kilometers. All right. So our target is therefore is lastly to extract to use these points to extract the pixel values coinciding exactly with those points. So to do that, we can say our statistics for our regions of interest, we will reduce the S2 image for regions, right? So we use reduce regions, okay? And in reducing region, we provide a collection, and our collection are the points, right? Then other than collection, the next thing we are interested in is scale. So we put the native scale for Earth Engine. Something is not right. We sample regions. Sorry for that. So in sampling regions, that is when we are getting the point coordinates and we don't need any reducer for that, right? So that is correct. And then we then get our stats, and for these stats, we can convert it to a data frame. So we can say stats data frame gets stats, and then convert it to EE as SF, make it an SF object. After making it an SF object, and then drop geometry. So st drop geometry. Okay. So that will take some time because it's doing the extraction of all our bands. Remember, we had like 11 bands. So each of these points is getting for the value for band 1, band 2, band 3, band 4, band 5, band 6, up to band 11. This is doing the same. This is doing the same for all the 26 points. And then bringing that feature collection into a simple feature and then dropping its geometry so that we only have stats df, which will basically be a regular data frame with all the spectral values and the ID of each point, like A, B, C, D up to Z. It doesn't have to be A, B, C, D up to Z. Yours can be 1 up to 100 or 1,000 or 1,000,000. Your points can be different from mine. Let me expand this so that we see the full table. Right, so these are the pixel values for each of the points. And then you can use this to train your model. For example, all these were T points in your case. And then you have other points which are not T or water body or whatever. You can extract them and bring them into your local environment. This is a regular data frame, and you can save it to your local disk, like write CSV, and then you have it. Okay, so that's what I wanted to share with you today. Thank you so much for your attention. I hope you enjoyed this. If you want to extract pixel values for anything, any image, whether it's night light, whether it's altitude, whether it's elevation, or whether it's slope, or whether it's whatever image is out there, cropland, whatever you want to extract, forests, you can get the pixel values simply in R without going to your Google Drive or going through a lot of processes of extraction. Super simple workflow. Okay, I hope you enjoyed this. If you know somebody who is interested in this, please share with them so that they can get to know how to get their pixel values from whichever points they were. You went to the field and you forgot to collect some points values data, please, you can simply get them through Google Earth Engine in R and then proceed with your analysis without necessarily going back to the field to look for the data, right? Okay, thank you so much. Please feel free to share this with your friends, and remember to cite all the data sources accordingly. For example, here we have used Sentinel data, so you need to acknowledge them in your work. We've also used a couple of packages. You need to appreciate the effort that these people make by citing them accordingly in your work. Okay, thank you and happy coding. Bye-bye.